high temperature, right? And then YT minus 1 will be the high temperature tomorrow. So we call, okay. And N plus 2 is the daily, that's the high temperature the day after tomorrow. So like this. So we call N is the forecast orange, and then H is the lead time. And so we put a head here. So this is a notation. You have head here, means forecast here. So YN plus H head, we call the H step ahead forecast. If you do N plus 1 head, this is 1 step ahead forecast, 1 day forecast. N equals 2, that's 2-day forecast, right? So 1 step ahead, 2 step ahead. So this is the notation, the forecast. And then you have to write this way. So this is your data, last data, or the forecast orange here. And then this is the step ahead. So this is 1 step ahead. So basically this is the edge here. And then, so this is the true value. And this is your forecast value. The difference we call forecast error. Okay. And now we want to do, so how can we find the forecast? See, suppose you have stationary time series. So suppose YT is stationary, and you know, say YT mean is 0. And then the ACVF, the autocovariance function we call gamma K. So you know gamma K, you know the model for YT, and then suppose at this moment mean is 0, right? And then there's 2 methods you can do the forecast. So 2 methods here. The first one called the minimum mean square error predictor, or you call this a conditional expectation predictor. So basically, so this is your data have. That's your data you have here. And YN plus H, you want to forecast the value for YN plus H. So you take expectation. So expectation of this future value. So given Y1 to YN, that's the data you have. So this is a typical value for YN plus H if you know or given Y1 to YN. So we call this is the minimum mean square error predictor, or said this is because this is a conditional. So this is conditional expectation. So it's also called conditional expectation predictor. So that's the first one. The second one, we have linear predictor. So linear predictor says, this is your forecast. See, I have Y1, Y2 to YN, right? That's all my data. So I just take a linear combination of all the data. See, if you want to predict tomorrow's high temperature, okay, and YN is today's high temperature, and this is yesterday's, right, high temperature. So you may give more weights to say today or yesterday, because you think like yesterday, today are highly correlated with tomorrow's temperature, high temperature, right? And then the question is, how do you determine those coefficients here? But this one we call the linear predictor. So one way we choose the coefficient or the weights for the linear predictor, so we minimize, this is a forecast error, right? Forecast error squared expectation. So that's a mean squared forecast error or mean squared prediction error. So we forecast this mean square error, and then we can choose the coefficient for this linear predictor. So we have 2 ways to do the forecast. So 2 methods, which one is better? Or in general, so which one you should use? Okay, so we know the first one, conditional expectation predictor, theoretically is better than a linear predictor. But in practice, linear predictor are easy to compute. So you can easily compute the linear predictors, and then also sometimes it's hard to find the conditional expectation. So, but theoretically, this is always better than the linear predictor. When you have Gaussian time series, so like each YT is normally distributed, and then the two predictors are equivalent. If two predictors are equivalent, if linear combinator predictor, so this one here, you can easily find the coefficient, and then linear predictor are much more easier here. Okay, so the first one. So the minimum mean square predictor or the conditional expectation predictors. For example, okay, if you have this AR1 process, right, and phi is given, and sigma e squared is given, and we know the phi absolute value must be less than 1, so for YT to be causal, right? Okay. Now we want to find one step ahead prediction forecast, two step ahead forecast by the conditional expectation predictor method. So we start with, so when you see something like this, so this means you have data y1, y2 to yn. So what is my one step ahead predictor or forecast? So this is the conditional expectation of yn plus 1, right? Given all you have, so that's a y1 to yn. So we want to find this conditional expectation. So we plug in. So yn plus 1, we can find from here. So that's yn plus 1. So t equals n plus 1 here. So phi, so t is yn plus 1 minus 1, that's yn, plus n plus 1, given everything here. And conditional expectation, so the first term, so that's phi yn, given this, plus second term expectation n plus 1 okay. So we know by the definition of AR1 here, the white noise term is always uncorrelated with the past values of YT, right? So give you y1 to yn here, and then expectation of y noise, because the y noise n plus 1 is uncorrelated with y1 to yn. Expectation, this conditional expectation, just expectation. So this term here, just expectation of en plus 1, okay? When you take conditional expectation, this equals just the expectation of x if x, y are independent, right? So this term, the second term, just expectation of y noise at time n plus 1. And then it is y noise. This notation here means mean is 0 anytime. So this one is 0. So the second term, so this is 0 here. And then the first term, so phi, so we know that's coefficient, right? And then expectation of yn given y1 to yn. See, if you already know yn, so you take expectation of yn. So just like a constant, you take expectation still constant, right? So this just yn because you already know. So this just yn. So one step ahead forecast of AR1 process. So yn plus 1 hat just phi times the last observation yn. So that's your, so basically, so you want to, if you have AR1 process, you want to predict tomorrow's high temperature, you just use the coefficient times today's high temperature. So that's a one step ahead forecast. Question? Okay, we do one more. So if we do 2 step ahead forecast, so yn plus 2 so here's yn plus 2, right? And given y1 to yn. So 1 plus 2, so from the AR1 different equation, you have yn plus 2 equals the yn plus 1 plus en plus 2. And given y1 to yn. So the second term, expectation of y noise at time n plus 2 given data y1 to yn. So this term expectation is 0, right? Again, the y noise at n plus 2 is uncorrelated with the past values of yt. And then the first term, so we have expectation yn plus 1 given y1 to yn. This one here, we just calculate this one, right? By definition, this is the forecast for n plus 1. See, yn plus 1 had, you use the AR coefficient times last observation. The observation right before time n plus 1, that's yn, right? You know yn, okay. And when you do yn plus 2 forecast yn plus 2. So you have the same coefficient here and here. You want to use the last value. So, but you don't have it. So the last value, say, if you do have a yn plus 1 here, you can calculate this one, right? But we don't have this. You don't observe or you don't have this one. So you replace this by its forecast. So you put the head here by its forecast. And then this equals phi yn. So that's just phi squared yn. So if you see this pattern in 3 steps ahead, so 3 is phi cube yn, right? if you put, say, n plus h hat, so you have it right here. So this is for AR1, the forecast for AR1. Question? Okay, so now linear predictor. So linear predictor, we have a stationary time series, mean zero, autocovariant function gamma k, and if gamma zero is the varies, right? If varies is positive, and then your ACVF autocovariance go to zero as k go to infinity, means, see, you have correlation, see, YT, maybe YT minus 1 or YT minus 2, but this, when this k go to infinity, so you have two observations if they're far away here. So the correlation just go to 0. And then the best linear predictor for yn plus h from the data y1 to yn is, so this is the formula, linear predictor, right? And then a vector just out coefficient. So this is a solution of this equation here. So this Yn is the variance covariance matrix. So this gamma n, sorry, this gamma n here, gamma n is the variance covariance matrix of Y1 to Yn. So this means, suppose you have you just have three observations. And then the gamma 3 variance covariance matrix of Y1 to Yn. So this is 3 by 3. So the diagonal is the variance of each YT here. So the first one is variance of Y1, right? Variance of Y1, that's gamma 0, that's variance. So the stationary, so gamma 0 on diagonal. So variance is constant. So diagonal, that's varies. Off diagonal, that's covariance or autocovariance. So for example, this one. So this is the covariance between Y1, Y2. So we call gamma 1 because the time difference between 1 and 2 is 1. So that's a gamma 1 here. And then you have covariance between Y1, Y3, so that's gamma 2. Symmetric is gamma 1, gamma 2. And what about this one here? This is a covariance between Y2, Y3. So that's a gamma 1 here. You have gamma 1 here. So gamma n is the variance covariance matrix of Y1 to Yn. And then A is the coefficient. And this one here, this is the vector for autocovariance. So you start from gamma h here. If you want to do one step ahead, so if you want to do one step ahead forecast, so you have 1 here, h equals 1, and then this ACVF vector, so you have gamma 1, gamma 2, gamma n minus 1. So if we have n3, so we have 3 observations. So h equals 1, n equals 3, minus 1, you have gamma 3, right? So this is just a 3 by 1 here. And then you need to solve, say, A from this equation. You have gamma n here, that's your variance covariance matrix, and then this vector, so right here, and solve this linear equations. Okay. So to solve this one, so this equation here, basically you multiply from left the inverse of gamma n, right? You have inverse gamma n here. So this is, and then the left-hand side right here, this is identity matrix, right? So you have A left, and then this is the right-hand side. So that's your solution. So gamma n inverse, and then this is the vector for ACVF. Okay, so now you got A here, and we have the condition here. So this condition means your variance occurrence matrix, this one is invertible or is non-singular. So if this one here in gamma n is full rank, non-singular, invertible, so basically you can find this gamma n inverse. So this exists. So this is a condition. And then we have learned the ARMA model, right? The last chapter unit, we have the ARMA model. So ARMA model stands for stationary time series. And we also called, so if you have causal ARMA model, and causal ARMA model, we call short memory. Short memory stationary means, see, k from 0 to infinity, absolute value of all your auto covariance here, gamma k. So this sum is finite. So if this sum is finite, and then you can have, see, gamma k equals 0, so when k is large. So that means if you have causal ARMA, and then this condition is satisfied, and then you can find this inverse, gamma n inverse, and then you can compute the coefficient vector A. So if you have causal ARMA, you can go ahead to use the linear predictor. Things you can do, you have solution, right, of this equation here. And then we define another. So we define the mean square error here. So forecast error square, take expectation, we call the mean square prediction error, okay, or MSE. Okay, so I give you out just the result. We don't do the proof in this class. So this is your variance minus, so this coefficient A here, transpose, so this means transpose, A transpose n times this vector for ACVF. So we can calculate the mean square error. So for each forecast, you have a mean square error associated with that. Okay, and then okay, so this is the mean square error. Right here. Okay, we have this mean square error here. The formula a little bit different. So you have gamma 0 the same, this is same here. And then we plug in A transpose. That's A here. You take transpose. So A, if you have two vectors or matrix, whatever, you take transpose, and so B transpose go first, and then A transpose. Okay, so you have this transpose go first right here, transpose, and then gamma A inverse transpose. So A inverse, you take transpose, is still A inverse. So transpose, and then times this gamma n right here. So that's the mean square error. See, gamma k's are given, right? We do the linear predictor. We said you have a stationary mean zero stationary time series with mean zero and ACVF gamma k. So gamma k is given. So basically gamma zero is known, this vector is known, this vector is known, this variance cross matrix just includes varies on diagonal and then ACVF off diagonal. So it means everything here is given. So you can calculate this mean square error. Okay. Questions? Okay. So forecast error. So this is forecast error, right? So on average, the forecast error is 0. So expectation of forecast error is 0. So this forecast is unbiased. And then, so forecast error, so each observation, so here, that's each observation, right? Yj from 1 to n, so that's your observation. This is the forecast. So expectation equals 0. So this expectation equals times expectation of y if x, y are independent or uncorrelated. So in this case, we know yt is mean 0, right? So mean 0 here, so expectation of the product is 0 here. So the forecast error and your observation are uncorrelated. So your data are uncorrelated with the forecast error. So in about all the calculations we have, we assume mean is 0, right? But most times, so your time series mean is not 0. So if mean is not 0, so you just subtract mean from the original time series to create a new time series we call xt. So that's the mean time series. So xt, so xt now is mean 0, right? And then say you subtract mean is a constant. It won't affect the variance. That won't affect the autocovariance. So the autocovariance for x, autocovariance for y, so they are same. Here the same, and you have 0 mean time series here. And then we know this one here. So that's gamma n inverse times gamma. Thing we put something here, right? So the n here, see the gamma n inverse and gamma n, see at here, so the vector, so they all just include the ACVF. So the coefficient only depends on the ACVF. So the forecast for xt, so we replace all yt by xt. And we have the same coefficient here, a1 to an. Okay, or so you see, basically this one is forecast for y minus mean, right? And this is just your data subtract mean. You plug in here. And then, so you do this one first. You subtract mean first, do forecast, and then add the mean back. So this is the forecast for the original with mean mu here. Okay, so we have two prediction method or two forecast method. linear predictor or conditional expectation predictor. So for linear predictor, so the linear predictor, this equals, like I said, this gamma n inverse this vector. So think about it. If you have sample size n, say, if you have daily data, that's 365, right? If you have for 1 year, so see daily. So 1 year you have 365 about. So if 10 years data, so 10 years daily data. And then the gamma n here is 3650 by 3650. This matrix. And then you have to take inverse. Take inverse of a matrix, say like 3650 by 3650. So this is not easy job to do. So to avoid here calculating the inverse of a big matrix, so we have two algorithms. So one we call the Durbin-Levinson and then innovations algorithm. So now we want to calculate, see, basically the linear predictor, you need to find the coefficient, right? A1 to AN. So we can use these two algorithms to compute the predictions recursively. So it means we don't need to calculate the inverse of a big matrix of gamma n. So the two algorithms. So the first one we call the DL algorithm. Okay, now DL algorithm can be applied to, see, YT must be mean 0 and stationary. So if you have stationary time series mean 0, you can apply DL. So if mean is not 0, that's okay, right? You subtract mean, make a time series active with 0 mean. But YT must be stationary. Means if your time series non-stationary, you cannot apply the DL algorithm. So you need to have a stationary time series. And variance constant and gamma k go to infinity. So this means, so we just know the ARMA model, right? So all ARMA model, causal ARMA model satisfy this condition here. And we have the linear predictor. So this is just one step ahead. So one step ahead. Okay. Phi n1, phi n2 to phi nn. That's the coefficient. And I don't know if you remember our notation for partial ACF. We use notation phi kk. That's the partial ACF, right? So all the coefficient here, this one, this is just the partial ACF at lag n. So k equals n. So here, this is the partial ACF. And then the mean square error of this forecast. So the same as the forecast error square take expectation. We call this Vn. Okay. And then the DL algorithm so works as following right here. So we start with, so y1 hat. So what is y1 hat means? So y1 hat, so suppose you have nothing, you don't have any data, and you want to predict. How do you do it? So you don't have data, and then you want to predict the next value. And then you just use the mean of the process, right? So the mean process is 0. So we just use 0, the average for y1 hat because we have no information, we have no data. So we start with y1 hat equals 0. And then V0 is the forecast error. So this one, so this expectation of y1, that must be your true data. So n equals 0 here means your sample size 0, you have no data, right? Minus y1 hat. So y1 hat n take square. So that's V0, right? So y1 hat is 0, so that's expectation y1 squared, so that's gamma 0. So we start, so means, okay, we start with n equals 0. So y1 hat 0 with, so that's process mean. So your forecast is process mean. Your mean square error, the mean square forecast error, say this is just varies gamma 0, the process varies, process mean, process varies, right? We start from here. And then we calculate n equals 1, n equals 2, 3, and so on. So here, step 2 to 4 right here, we just repeat this 3 steps for each n. Okay. So for example, okay, now we start with this is n equals 0. If n equals 1, we start with this phi11 here. You start with phi11, so you have row 1 minus the j from 1 to n minus 1. So n equals 1, 1 minus 1 equals 0. So j from 1 to 0, so the sum is 0. So the top just row 1 minus 0. In the denominator, same, this is 0 here. So that's just 1 minus 0. So phi1101, I think that's by the definition of partial ACF, right? So you calculate row 1. And then you're, okay. So when n equals 1, that's your forecast right here, right? So n equals 1. So basically you want to do y2 hat, right? That's y1 plus 1 hat equals phi11 yn. Yn, so n equals 1, you have y1 here. So we start with n equals 0, we don't have any data, we use process mean, process variance, right? When n equals 1 means you have only one observation, so that's, you have only one, y1. So in here, your y2 hat, or y1 plus 1, so that's y2 hat. A linear predictor here, just phi11 times y1. So n equals 1 here, right? So you calculate your phi11, so you plug in here, you know y1, you calculate y2 hat. And then you go back, so n equals 3, n equals 2, now you have y1, y2, 2 observations. And then you start here, you do phi22, you calculate phi22, right? So your y2 plus 1 hat makes y3. So you have phi, so n equals 2, so phi21 yn plus phi22 yn is y2. Phi22 y1. So you need to find the 2 coefficient. You use this formula to find phi22, and then this one here is phi n. So when j equals 1, you do phi21. You set j equals 1 here, and then you find a phi21 right here, this one here. And calculate this mean square error. So that's for n equals 2, and then you go back to calculate n equals 3, and So we call this recursive algorithm. Okay, let's do one example here. Okay, we still do AR1. Okay, the same example. Okay, AR1. Phi absolute value less than 1, y noise 0 sigma e squared. So we calculate one step ahead forecast by DL algorithm, and we calculate its corresponding mean square prediction error. Okay, so for AR1, so we know this, right? Rho k equals coefficient phi power k. Okay, we start with n equals 0. And process mean is 0 here, and V0 is the process varies. For AR1, this is the process varies. And we do m equals 1, so you have only one observation. So you y1 plus 1 hat, which y2 hat, phi11 y1, right? So that's a phi y1. Because we know phi11 partial ACF just rho 1. So given, so AR1 coefficient rho 1 is just phi here. Okay, and then we can calculate Vn, which is V1 equals Vn minus 1, V0, 1 minus phi nn. So that's phi11 squared. So we just plug in all the numbers here. See, you V1, just the y noise varies. And then we do n equals 2. So y2 plus 1 hat. So that's y3 hat. This time you have two observations, right? Calculate two coefficients here. Okay, so phi22. So by the formula, you can plug in all the numbers here. For AR1, phi kk equals 0 for all k larger than 1, right? So partial ACF for AR model, phi kk equals 0 for all k larger than p. For ARP, so k larger than p, phi kk equals 0. So in this case, p equals 1. So phi22, we know that's 0. And then you find phi21. So phi21, okay, right here. So phi21 means n equals 2, j equals 1. Equals, so the first one here, n equals 2, that's phi1, j equals 1, phi11, minus n equals 2, right, phi22. N is 2, so n minus 1 is 1, and n is 2, j is 1, so phi11. So this is a formula you find phi21. So we have this one right here. And then we know phi22 0, so phi21 is phi here. And V2, so the previous one, V1, 1 minus phi22, phi nn squared. Okay, so this is 0 term, so V2 equals V1, so still same here. And then, so do n equals 3, n equals 4, so all you have is just this. This for AR, you only use the last observation. So yn plus 1 hat, just coefficient times yn, so we got this result before. And Vn, mean square error, so that's just the y noise varies. So DL algorithm is nice for AR model because phi kk equals 0 for any k larger than p. But for MA, it's messy here. So this example, we have MA1 process, right? Right here, theta equals negative 0.9. And then y naught sigma e squared equals 1 here. So we have three observations. We have three observations, and then we want to predict the next one, y4, and calculate its mean square error. Okay. So we start. So okay, this is all the basic information for MA1. MA1, that's theta sigma e squared, and we can calculate the rho 1 by this formula here, which is negative almost 0.5, and rho k equals 0 for all k larger than 1. And here's the MA1 varies. Okay, so we got all the numbers here. So start with a equals 0 means process varies. We just calculate as 1.81, right? A equals 1. So y2 hat or y1 plus 1 hat equals phi11 y1. So that's the same for each algorithm. And you plug in, because phi11 equals rho 1 by definition. So you plug in this one here. And that's your observation, so that's your forecast for y2 hat. So you already have y2, you don't have to calculate this, right? So this number, you don't need it as your final result, but you have to use it to do the recursive calculation here. So you do V1, so that's previous one times 1 minus phi11, so phi n squared, okay, right here. And n equals 2, you need to calculate 2 coefficients. So so now this time phi22 is not 0. You have to use your rho case here, so this is negative. And then phi21, so use this formula, so you got this one here. You can calculate V2 here. Okay, so and then you do V angle 3 and so on. You don't have a formula for this. So once because we have sample size n equal 3, right? We have sample size n equal 3. So we want to predict y4 hat. So if you have a sample size large, so you have to continue this process. But for this example, we only have 3 observations, so n equal 3. So we need to find the 3 coefficients here. So just use the follow the formula in V3 here. Okay, so one thing you can see from here, okay, what is, okay, now this is your final forecast. You want to predict Y4, right? So this is Y4 forecast. So one step, okay, predict Y4, use 3 observations, and this is one step ahead. And this is the forecast value here, 0.55. That's the value for the forecast. And then V3 is the MSE here. So we want to find the forecast for Y4 and then the mean square error for this forecast. So we have this one here. See, this is right here. You want this one, right? And this is right here. This is right here. So I think that every time student has mistake. Okay, so calculate. Okay, predict Y4, right? So you need to find this, or this is 3 plus 1 hat. So this is what you need, a one step ahead forecast. And then find MSE. So you need V3 here, not V4. So you need a V3 here. So you need Y4 hat and V3. That's V3 here. And this is UY4 minus UY4 hat. So that's a V3, not V4. So the MSE associated with Y4 hat is V3. So we have, okay, this is what we need. That's your answer. Y4 hat, this is the MSE. So if you don't have any observation, you do the forecast. Your mean square error is 1.81, right? You have one observation, your forecast mean square error 1.362. If you have two observations, and then this forecast mean square error is 1.215. You have three observations, and this is 1.144. So you can see the pattern. So the mean square error is decreasing, right? Because once you have more data, and then so your forecast so it's more accurate, and then your mean square error is smaller. So you have the Vn, V0, V12, Vn, V3. So you see this is decreasing as more data you have. Okay. So this is all for today, and then Thursday we'll do the innovations algorithm. So we have 15 minutes. So like every Tuesday, so I leave 15 or 20 minutes for questions for homework. So your homework 3 due tonight, right? So if you don't have questions, you're free to go, and I see you on Thursday. And okay, so here's the homework. And then we have office hour today from 2 to 3. So I will be on Zoom from 2 to 3. So if you have any questions come up, so you can come back during the office hour. Okay, any questions about homework?
I do have some problems with problem 1.
Okay. Which one? A, B, C, D, E?
All of them?
In general. All of them?
Yeah.
Okay. So this question asks you determine which one, causal or invertible, right? So the two things, so these two concepts are important. So when you do forecast or fit model, so you have to understand those two terms. And then in some book, they call the causal time series they just call stationary time series. So in some books, they use the different terminology for causality. Okay, so if time series is causal, then stationary. So the conditions or how to determine a given time series is causal or invertible. Okay, first thing, all MAs are. So we know all MAs are stationary, right?
Yeah.
Okay, and then if you see the definition for MAQ, so that's ET minus 1. So theta Q, ET minus Q. Okay, so causal means, so the causal time series means you can write your time series. You can write your time series in forms of this. So all Y noise at current time, T, and past time. So t minus 1, see you have current time t minus 1 to t minus q, right? So, and then your yt only depend on the current and past values of y noise. We call this as the causal time series. So for all MAs, stationary and causal. So if you see MA model, so that's causal. So you don't have to check anything. If you have MA, that's causal. Okay, that's first thing. And then AR model, see you have YT equals V1 YT minus 1 plus see VP YT minus P plus ET, right? So if you move everything, so you move this one, everything to the left-hand side here. So you just YT subtract everything here equals ET. Invertibility means your Y noise depend on current time T, current time Y value, and the past Y values. So for all ARP is invertible. So ARP is invertible. Okay, all MAs are causal, all ARPs are invertible. Okay, so the first one, okay, now this is the AR2, right? Second one, this is ARMA what? You have to determine the order here. This is ARMA. See, you have E1, ET minus 1, you have 1 here, right? So it is AR part is 2 or 1? That's 2, right? Because you have
yeah, I do see a 2 at the front.
Yeah, you see YT minus 2 here, so that's ARMA 2 1. And second one is ARMA. So you see YT minus 1. The last
you mean the third one?
Yeah, third one. Yeah, see here. So that's 1, right?
Yeah, there's a 1 at the front, and there's another 1, and then a 2.
Yeah, that's 2. Yes, that's ARMA 1 2. And part D, that's ARMA 2 and 2, right? And this one is ARMA 2 and 1. Okay. So the first one, AR2, and we know it's invertible, right? You don't have to do this part. You just need to check if this is a causal. And then for part B to E, you have to check both causal and invertible.
You're saying A is causal?
So yeah, A is AR2, so it's always, sorry. So A is AR2, it's always invertible. And you have to check if it's a causal. Okay, so now you see all 5 here. So P is less than equals 2, right? Q is less than equals 2 here. So causal is only related to the AR part. Invertible is related to invertible time series. You check condition, it's only related to the MA part. So if you want to check a causal, so you have to find the coefficient for AR part. So for example, the first one, phi1 is negative 1.8, right?
Yes.
Phi2 is negative 0.8. And we have 2 methods to check the causality. One, you found the AR polynomial equation. So that's 1 minus phi1x minus phi2x squared. That's AR characteristic polynomial equation. polynomial. So you set it is equal, so that this equation, you solve this equation. It has two roots, right? You have x1, x2. Two roots, x1, x2. If both roots in absolute value larger than 1, if both larger than 1 in absolute value, it is causal. So you found the coefficient phi1, phi2, and then you solve this equation. You found the two roots. For the two roots, if both larger than 1 in absolute value, the time series is causal. Or, so this is the first method. So that's method 1. In method 2, so lastly we have 3 conditions. So you do phi1 plus phi2. If you check if this is less than 1, you check phi2 minus phi1, you see if this is less than 1. And then you check if phi2's absolute value less than 1. So check 3 conditions. If all 3 conditions are satisfied, and then the time series is causal. Okay, so for this one, phi1 is negative 1.8, right?
Yes.
Negative 0.8.
1.
So that's
Negative 0.81, I said.
yeah. So 2 negative, sum is negative, right? So then it's less than 1. So the first one is okay. Second one, so phi2. So phi2 is negative 0.8. And minus phi1, negative 1.8. Well, this equals 1, right? So 1 is not less than 1. So this one is not satisfied. Oh, sorry.
Wait, can you leave this up for a second so we can just write it down really quick? Even though you know, as an...
Say that again?
I was just asking if you could leave the green part up really quick so that we could write it up, the green and the brown part that you just wrote down.
Sure. Okay, I think I forgot this one here. There's one here. That's 0.81, not 0.8. So, sorry. There's one here, right? And then 1.8. Okay, so see the difference here? That's 0.99. Yeah, 0.99. And 0.99 is less than 1. So sorry, this is right here. And then phi2 absolute value. Phi2 is negative 0.81. Absolute value 0.81, less than 1, right? So all 3 conditions are satisfied. So the first one is causal, and AARP is always invertible. So first one is causal and invertible. I think we have okay. Let's do just one more.
And then we'll finish it off on the office hours.
Yeah. So yeah, you can come back during the office hour.
Okay, so the first process is causal, and the second one is invertible.
Second one. Okay.
In part A.
Yes, for part A, yes. Causal invertible. Yes. And then, so, let's see. Like I said, the invertibility is just related to the MA part, right? If you have if MA part is MA1, your theta absolute value must be less than 1 this is less than 1 and to be invertible. So second one, see this one, the theta here is larger than 1. So second one is not invertible. So, okay, invertibility, you just use the MA part. So MA1, that's your condition, right? And if you have MA2, you need to check condition. So negative theta 1, negative theta 1 plus negative theta 2 less than 1. Negative theta 2. So this is similar to the 3 condition for AR2. Replace feedback theta, negative theta. So negative 2 squared less than 1. So replace phi 1 by negative theta 1, replace phi 2 by negative theta 2. If all, so for MA2, so if our model, the MA part is MA2, you check these 3 conditions. If satisfied, it's invertible. For MA1, you just have one condition here, theta absolute value less than 1 is invertible. So this is for invertibility. For causal, you just need to check the AR part. So AR part, if you have AR1, you need to do, for AR1, if phi absolute value less than 1, it's causal. AR2, so the AR part is AR2, you use this 3 condition here, the green one, to check if this is causal. And for higher order, say AR3, MA3, 4, so you don't need to know that. You don't have to do that by hand. So just the first 2 orders, AR12, MA12. Okay. So I think we have to stop here, and then so come back to the office hour if so you still have questions. And I see you all on Thursday. Thank you.
Thank you.
You're welcome.